The magnetic force on a charged particle is F equals QV cross B. Okay. Again, B is from sources, something else that's acting on this charge. Not to be confused with the fact that this moving charge is also creating its own B field, but that can't act on itself. This is from something else, so I've got to keep that clear. That can be confusing. All right, so this shows that a force can only happen if these have at least some amount of perpendicularity. Okay, if they're parallel to each other, then there's no force acting on this charge. And if they're perpendicular to each other, then the force is maximum. Well, that becomes very interesting if we are able to get the original situation to be perpendicular. So, for example, what if we have a charged particle, assume it's positive, moving that direction in a region of space, where the B field everywhere is into the page, or everywhere is out of the page. Sorry, so that's the dots. These dots means B is out. Okay, the direction of B is pointing out everywhere in this space. Okay, well, by the right-hand rule, well, first of all, these are perpendicular because this is moving in the plane of the page, and these are perpendicular. So this is going to give us just a QVB, and the direction is given by the right-hand rule. So in this case, the right-hand rule is going to be this way is the velocity, the B field is out, which means my thumb is down. Okay, so the force, which is the result of the cross product, is down. All right? Well, that's going to make this thing curve down. It's going to curve down. Well, at some later time, it might be over here, moving like that. Okay? Well, what is the direction of the force now? Use your right-hand rule. It might be a little bit easier to turn the page so it's a little bit away from you. Okay? But I'm going to let you do that, and you'll find that the force is that way. And it'll be the same size because this was perpendicular, this force is perpendicular, so it can't change the speed. So the speed's the same, the B field's the same, so the force has to be the same. All right? Now this force is also perpendicular, so it can't change the speed, so it keeps moving the same speed, but does change direction. And we'll get something maybe over here. Let's say it's moving like that. Well, what's the direction of the force? If you use your right-hand rule, you'll get this way. And it's the same size again. Now, you could keep doing this, and you'll find that all the forces point inward. Well, guess what? That's circular motion. And in fact, that is a characteristic type of motion of a charged particle in a magnetic field, is they swirl around the magnetic fields. Okay? And so, if I were to, redraw this, I get this circular motion, okay? And it is moving at a constant speed, v tangential, and there is a constant force inward, which ought to be equal to MAR, which we know the special acceleration, radial acceleration for circular motion is v tangential squared over the radius of this circle. Okay. So let's go ahead and take that answer now and plug it into here to see what we can tell about this radius. So we know the size of this force is QVB. We know that force equals MAR, which is mv squared over r, and those velocities are the same. It's the velocity it had moving around the circle. You can cancel out one velocity, and we can do this. We can say, well, the radius of this motion is mv over qb. And so we can measure this. This is actually called the cyclotron radius. You can think of circular motion or cyclotron motion. The cyclotron is a device you can read about in your text that we use to do experiments with. But this would be the radius of a particle of charge q, mass m, moving with speed v in a magnetic field B. Or in other words, if we measure this radius, which we can, then we can determine the size of the charge over the mass. And we could use this to investigate particles. And we're going to do some examples about a mass spectrometer that uses these techniques. Okay. Now there's another thing we can play with this. Since it's circular motion, we can do some timing problems, or talk about the time it takes for it to go around. And we can say, okay, let's see. V is equal to, since it's moving in a circle, that's the same thing as distance over time. So we have m over qb. And distance over time is a circumference, so 2 pi r over the period. Okay, so we have r equals this. That means the r's cancel. And multiply the qb up. I have qb divided by the 2 pi m. 2 pi m. I'm left with 1 over t, which is 1 over the period, or that's the same thing as frequency. And we call this the cyclotron frequency. And this is the frequency at which these charges go around. And that idea of a frequency at which a charged particle is flying around a loop is used in lots of different medical imaging techniques, because there's charged particles moving around in our body, and we can put a magnetic field around them, like in an MRI machine, and we can actually sense how things are moving. We can take pictures inside the body because of the signals that come from these moving charges inside this magnetic field. Really, really powerful technique. And so the main idea I want to emphasize is, here's the force, which if they're perpendicular just becomes QVB, but it's circular motion, and it always will cause circular motion, which means we can relate it to mv squared over r, and therefore play around with some of those values.